So Sego, Sewa Guego. Hello, everyone, and welcome to another episode of STOODIS Science, Indigenous Scientist Chats. If you don't already know me from before, my name is Jenna Barnhart, and I'm the Indigenous Research Assistant for STOODIS Science. If you joined us last week, welcome back. But if this is your first time joining us, we're happy that you're here. If you've never heard of us, STOODIS Science, we are a subsidiary initiative launched out of Ryerson University's Sci Exchange program in 2019. Our objective has been to promote science outreach, science knowledge mobilization, and knowledge translation combined with traditional Indigenous teachings to Indigenous students. Throughout the years, myself and my partner in crime, Amber Sandy, have been working hard to offer science outreach programming specifically to Indigenous youth. If you're interested in hearing more about our past and future programming, you can find us on all social media platforms under SciExchange at SciExchange RU or at our website shown here on this slide, or you can just Google SciExchange Ryerson. For this event, we've partnered with our friends at Let's Talk Science to showcase three amazing Indigenous scientists in three separate talks. So today is talk 2. And on this program, we're welcoming our speaker, Corey Gray. Corey's a Scottish and Blackfoot from the Siksika Nation. Sorry if I mispronounced that, in Alberta, and he holds a degree in physics and applied mathematics from Humboldt State University in California. Welcome, Corey.
Hi, welcome, or thank you, Jenna. And a big shout out to Jenna and Amber for this invite. And a big thank you to STOODIS Science, Ryerson University, Sci Exchange, and Let's Talk Science. Thank you so much. Are you talking anymore, Jenna, or am I just going?
Oh, you're good to go, yeah.
Okay. Hey, good morning, everybody. Well, it's morning for me. It's 10 o'clock here on the West Coast. So I barely just got up a little while ago and took a shower, ironed my shirt and everything. So I'm just getting ready here. Let's see. So last week was an awesome talk by Joseph. And next week we have Dr. Nelson Hilding, who's also going to be talking about astronomy. So that'll be also very cool. And what I will be talking about is some of the work that I do, which is also astronomy related. So in the invites for this talk, I believe you have a packet that has problem sets. So we want to have those out so we can work through those. You'll need a calculator because we're going to just go through a couple equations, solve some equations right at the beginning. Okay, that's a joke. I'm kidding. So what we're going to be doing now is going to be very chill. It's going to be very, hopefully fun, and I hope it's interesting. I'm not a poet. I'm a hesitant or a reluctant speaker, so I'm not really comfortable sometimes. I used to be very shy and I hated giving talks, but now after lots of practice, I've gotten better. So that's one lesson I could share with you. Just practice does help. But since I'm not a good poet, there's a lot of visuals that I have. So I'm going to share a lot of slides with my talk. So I basically just a PowerPoint, and we're going to go through that because a lot of the concepts that we're going to be going through are kind of out there and they're kind of hard to visualize. So that's why I use images and videos and audio just with my talk. So yeah, so I think let's just get into it because I have so much stuff that I like to cram into this because there's so much I want to share with you. It's not just the science, it's also how I integrate my culture into this Western science. I mean, back in the day before my work made the news around the world, I still brought my culture to my work, whether it's going to Indigenous communities nearby and sharing the science we do. That's one thing. But I've also learned it's also important for Indigenous scientists just to get out there so that Indigenous youth can see options for what they might want to do in the future. So when I was young, I didn't see a lot of Indigenous scientists out there. So that's one thing I think about when I do this. So even though I'm shy and I don't like to public speak, I get over that fear because we need to get out there because we need more Indigenous youth in science. So with that, is there anything else I want to say? before we switch to my PowerPoint. Let me switch to the title slide really quick, and then I'm gonna have a drink of water just to go. Let's see. And, oh yeah, that's what I wanted to also talk about. Okay, so I'm hoping you can see my presentation now. Yeah, my title slide, I hope.
Yep, looks good.
Yeah. Okay. So, and you probably see me as well on the side, hopefully a small image so you don't have to look at my my sloppy self. Let's see, what was I gonna say? It's just, yeah, the last year and a half has been tough just because of Zoom, as we all know. I mean, I would have loved to have been able to speak in person for all of you. But that's another good thing about Zoom, is that I can still talk to you from my house in Washington State in the US. And so, yeah, here we go. This is a picture here of my work on Valentine's weekend when we had our last snowstorm. I took, this is a picture of a part of our detector, gravitational wave detector. And on the right is me, is my tracks from cross-country skiing 2 kilometers down to this building that's right here. And then here is coyote tracks, and here's rabbit tracks. So let's see. I'm gonna just jump into it then. Okay, so this is, I'm not sure if everybody's familiar with the Blackfoot tribe, but that is, this is the Siksika Nation. So the Blackfoot Confederacy consists of 4 bands of Blackfoot, and I'm going to talk about in a sec, but this is Siksika Nation, where I'm from. This is the West End, a place that I love to go ever since I was a kid. And really briefly, I'm just going to talk about what I'm going to be speaking on, Indigenous, ways to integrate my culture into my science, general relativity, gravitational waves, my favorite detections. If I'm a big chatterbox, I might just talk about one detection, but if I have time, I'll talk about my 2 favorite detections. And then just the whole concept of bringing yourself to whatever you're doing. It could be your career, it could be your studies, just bringing your culture and being proud of it and just getting it there, putting yourself in your science as well. But it doesn't have to be science, it could be whatever you're doing right now. And then I'll end with just some new things that are happening with us. So let's go. Yeah, so this is the west end of Siksika Nation. And like I said, the Blackfoot Confederacy consists of 4 bands of Blackfoot. So there's the Gaina, there's the Piikani, the Siksika. Those are the 3 that are in Canada. And then in the US, there's the Amskapi Piikani, which are the Blackfeet in Montana. And then in this image, the green area is roughly the traditional area, excuse me, of the Blackfoot people. I think it's conservative. I think we used to be a lot larger than that. We were a Plains tribe, and we were kind of a warrior tribe as well. So we kind of fought everybody and had a lot of enemies. It's not like that now. So yeah, so that's my tribe. And then I like to just share with my family. So in the center is my mother. Her name's Sharon Yellowfly. And then the kid with the chubby cheeks is my uncle, Sherman. And then these are my grandparents, Percy Yellowfly and Cecile Yellowfly. I just like these old photos of my family. Another family member is my grandma's father, Alphonse Slay. He gave me my Blackfoot name, which is Agaposuis, which means many weasel tails. This photo is one that my mom took at the Calgary Stampede, probably in the 1960s. And I like putting it in here because of this teepee. Really, I'm gonna pause really quick. Just Oki is how you say hello in Blackfoot. And so I just wanted to, I meant to say that at the very beginning, so sorry about that. So Oki is how you say, well, hello, or it's welcome in our language. So back to this teepee. I'm showing this on here because Alphonse was given this teepee by another relative. His name was Chief One Gun, and this is actually a star teepee. So it's a red teepee with yellow circles on it. And all of those represent stars. And I like to have that on here because something I've learned is that a lot of our teepee designs integrate astronomical concepts into the design. So you'll see stars, moon, sun on teepees. And there's a reason why, because if you're ever on the reserve in Siksika or anywhere in Blackfoot territory, as with a lot of indigenous areas, the sky is so big and it's so dark, and you could see the stars so bright, and it's easy to understand why the sky is important to us and why we have teepee designs, why we have a lot of stories that are about the sky, and a lot of those things, what we see in the sky. And another thing that I'm kind of more recently learning about are medicine wheels. And so this is an article from 2018 that I read about a medicine wheel that's on Blackfoot territory. This is one in Majorville. It's thousands of years old. And as soon as I heard about it, I knew I had to go visit it because I'd never been to it. I never heard about it before. So this is May 2019 where I went to go and check it out. So you can see this is what the plains look like. I think this is looking west towards Calgary and the Rockies. But it's a powerful place. And there's a lot of medicine in these, and you can feel it when you visit it. And that's what I've learned from other people as well. And the idea is there's piles of rock arranged in certain ways, and they're for ceremony, and they were also to look at the sky as well. So from this instrument on the plains, here is an instrument 20 miles out my window in the deserts of Washington State. So LIGO is where I work. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And this is where I work. I was there 2 days ago to do some work at the lab. And I'm going to talk a little bit about what is this crazy looking thing, this thing that looks like an L when you're on top of it, when you're flying over it. But really quick, let's take a drive down one of the arms. We're going to take a drive right down this arm here. These arms we call beam tubes, and we call them beam tubes because we send beams of light down both of these arms. So let's pretend we're photons and take a quick drive. So this is a 4-kilometer long arm. This building that's coming up, lots of tumbleweeds. This building coming up is 2 kilometers away. That truck is a liquid nitrogen truck. And then 4 kilometers away is the end station where we have an important mirror for us. And I'm going to explain what all this means later. But first, I'm going to return to my background and just give you an intro of where I started from. So even back in the day, I'm kind of surprised. I used to dress up and stuff. So this is me. I grew up a little bit outside of LA. This is my 4th grade class. I still have some friends from there that I still talk to and stuff. And then here is just kind of like my resume or where I came from. So Southern California is where I grew up. Here's a picture of me here. You could see I had braces. I like pizza. You could tell. You could see I ate a little bit when I was a kid. And this is my brother T, or Steve. And after high school, I went to Humboldt State University, which is in Northern California. I received 2 Bachelor's of Science degrees in physics and applied math. And I also did several internships during the summers as well. And as soon as I graduated, I didn't get my PhD. I decided to go to work. And so I was hired by Caltech, and I moved from California to Washington State. And that's where I am now. So I work at the LIGO Hanford Observatory, and I've had different roles as I've been here. Here's a picture of me in the lab of the building at the center of that L, which you'll find out more about in a little bit. So here's a picture of the West End again. This is me, my brother T, and my mom on Siksika on the reserve. And then here's my dad and me way back in the day. My dad was an electrical engineer. He taught himself. He never got a degree. He just kind of taught himself. So both my parents are role models for me. And then these are other coworkers that I work with. I'm an operator, a detector operator. And this is the operator team for the detector in Washington. And there's another detector in Louisiana that has operators as well. We're the ones who drive the detector. This is Sherman, my uncle, and he's visiting 2016, a few years ago. And then I mentioned my parents, and I have to mention MacGyver because MacGyver is also another role model. So when I was in high school, I watch this show all the time, and you guys, most of y'all are probably in Canada, so I had to throw this picture up because he has a Flames hat. Go Flames! But I wanted to be an Indigenous MacGyver, and so in the show you learn that he studied physics, and so that's what I did basically. So yeah, so from there, let's jump into the science now. So I mentioned general relativity earlier, and I'm sure most of you probably know who this gentleman is here. This is Albert Einstein. Keep in mind that date, 1915, keep in mind that date. And the general theory of relativity, or GR, Einstein presented his general relativity to the world in 1915 and put the world of science on its head by coming up with a completely different way of thinking of gravity. So before Einstein, gravity was thought of as a force. So you have masses and they have an attractive force between them, and that's what gravity was thought of. This is from Sir Isaac Newton. And there's the whole story of Newton sitting under a tree and an apple falling on his head, and he had the realization that the Earth's gravitational force pulled that apple and had it land on his head. So yeah, equations of motion from Newton can explain most of gravity, but there's extreme cases where it fails, and that's what Einstein couldn't deal with. So he came up with a completely different way of thinking about gravity. So instead of forces, gravity is thought of as the effect of a mass on the space around it. And so this picture here is showing you that effect. So you have a big object and a small object, star and a planet, and they're bending the space around them. The bigger object has a bigger hole that it's warping in the space around it, and the smaller object has a smaller one. My water bottle is bending space around it, but even very tiny. It's not a big effect. So it's bigger objects can bend space more. And that can even be done even more extreme. So moving from stars, there's other objects in the universe that can even bend it more. So if you take objects that are even more dense and packed in and very strong, very heavy, they have a lot of strong gravity. And so they warp space a lot more. And so that's what you're seeing here with the neutron star here. These aren't to scale. This guy would be about a very tiny thing compared to the sun. And I'll talk about neutron stars later. And then black holes are a completely different animal. They're not even matter. They're just areas in space where they bend space-time or the space around them just extremely, an extreme amount. So these are examples of heavy objects, the two on the right. And then, yeah, so I have to talk a little bit about black holes here. So, I mean, a black hole isn't matter. It's just this area in space where that area in the universe is bent very strongly because of the strong gravity because of this object called a black hole. And it's not matter. It's just this weird area that is it's just a place where funky things happen. Time is bent as well. Space is bent as well. Things fall into them. They make things move around them in certain ways, or they gobble things up. And so they're just kind of scary, and they're kind of very sci-fi-esque. So, I mean, I think of movies when I think of black holes, because you can't think of something as crazy as black holes. And then this video here is showing indirect effects of a black hole. This is a supermassive black hole at the center of our galaxy. And these are stars that are moving around because of something invisible that we can't see right around here. And so this is a video taken over 20 years, and it's looping. And so this is just showing you what black holes do. A big one, a supermassive black hole. Like I said, I like movies. So there's a movie called The Matrix. Neo here is sort of like a black hole because he's bending the matrix around him, and you can also see it wiggling and vibrating because of that power he has. So he has kind of the power of a black hole. And I always say, if there is a LIGO movie, I'd be happy if Keanu played me. Okay. So what we've been talking about so far is when an object is just out there in the universe and not moving, it's static. But what happens if you move that object around? What happens if you explode it, or if you take two objects and smash them together? This is what we have here, two black holes that are moving around in space, light from stars behind them, okay, right there, you saw these two black holes that just merged into each other. They crashed and they formed a bigger black hole. And there was a big vibration that happened. That big vibration is a burst of gravitational waves or wiggles in space-time from that collision. Those wiggles are what we're looking for. Those are what gravitational waves are. Einstein thought we would never discover them, a century ago, but a century later, technology improves. We learn about black holes and neutron stars, so things change, and I'll show you what happens. This is what we're going to talk about next. How do you detect these guys? These wiggles in space-time. That detector that I work at, this is a cartoon of it. The main thing to keep in mind or look at are these two guys here, these two circles. These are masses or mirrors, and our detector is basically just a ruler. And what we do with this ruler is measure the distance between those two mirrors. For our detector, they're 4 kilometers away. And so let's look at a video. So you have a light source. You have this guy, this is called an optic, and it's a beam splitter. And the light from the laser hits this beam splitter. You have 2 twin waves of light that go down each of those arms, hit a mirror. For us, it's 4 kilometers away. Those waves return back to the beam splitter, combine, interfere with each other, and then you get interference here. Right now, they're negatively interfering with each other, so there's no light. They're canceling each other out. But if you move those mirrors just a little bit, you get positive and negative interference, or light and no light. So little effects can be seen very easily on this detector here, and you could get information from the motion of those mirrors. And so we can look, or we can resolve over 4 kilometers, the length of that arm, we can look at distance changes of 1,000 times smaller than a proton. So that's a very sensitive ruler that we have. And we need that because gravitational waves are tiny by the time they get to the Earth and pass right through the Earth. And I'm going to go through this one more time, just to go from the beginning to end. So you have a source far, far away. Luckily, these 2 black holes crash into each other, generate gravitational waves. Waves move through the universe at the speed of light. They pass through other stars, other galaxies. They might be passing through other civilizations, other alien civilizations as well. They pass through everything at the speed of light, and they get smaller and smaller and smaller as they travel at speed of light. And eventually they pass right through the Earth, and we're kind of being showered by them all the time, but they're just so tiny that we never feel or observe their effects up until a couple years ago. And so this is where I work. This is the detector. And in that cartoon earlier, those 2 mirrors or masses are in these buildings 4 kilometers away. And so that's what the detector looks like. And then this is the corner station. Those mirrors look like this. So this is what a picture of one of them. And we have a coating on it to protect it and keep it clean while we're in there. We have to dress up like this to make sure we don't get dust on our mirrors as well. I used to have a dog, and we wouldn't want to have dog hair on that very expensive mirror. Here's another picture, a side view. So we were looking from the front. Here's the side of that mirror. We basically want these mirrors to float so that the only thing that moves them are gravitational waves. And so now we're going to zoom into that corner station building. That's what we have here. So these tubes, this tube here and this tube over here, head out 4 kilometers to those to the mirrors, and then the light comes back, and then we look at it over here. So the light comes back right here, and let's jump into this chamber, mainly just because you could see a picture of me inside of one of the clean rooms. These are detectors. These would look at the light and analyze the light so we could get information from it. Here's what the light looks like. We can take that light, turn it into a current or voltage or an electrical signal, and this is what it would look like. This is when the machine was running, this is what it would look like, and I'm going to try to make a sound of what it sounds like. So it's basically static right now. It's just white noise because there's no event that's moving our detector. And so most of the time, this is what the detector sees. So just random wiggles like that. So remember that a red wiggly line, because I'm going to talk about it later. And oh man, it's already 27 minutes after. Okay. Something I want to just take a side, just to jump off where I was talking about and just talk about what it's like to work where I work, and focus on the idea of someone comes up with an idea of something they need, and then going to having that idea in real life. So somebody wants something made, they ask an engineer, and then engineer makes drawings, and then we send these drawings to machine shops and they make parts, and then eventually you have this thing in front of you that can do things that you wanted. And so I'm just showing this because this is something I made. This is something called a beam diverter. And this is the drawing for it. And I just wanted to show you what it looks like. And basically that thing here would hold a mirror. I don't have a mirror in here, but this mirror moves like this. And this is inside of our detector, and it just protects our other equipment. And so here's a video of what it does. I hope this isn't too loud. Go ahead. One more time. It's doing something very simple, but this thing's inside of our vacuum system. So it's an important part of our detector. So similarly to that, being able to do the work that I do has gave me confidence to build things. And so just in my personal life during the pandemic, this was my pandemic project. So I had this idea of wanting to paddle a kayak. And so this is what I did last year. I bought a kayak. Here are the drawings for it. Here is the box it came in. And then here's the finished product. And so I finished that in September, and I've been learning how to kayak. And yeah, my work helped me do that, just doing things with my hands, which I like to do. Okay. So we talked about general relativity, we talked about gravity, we talked about Einstein now, and we also talked about gravitational waves and a detector that can detect them. So up until a few years ago, they'd never been detected. That all changed in the fall of 2015. And so I'm referencing movies again. And yeah, so this is my favorite detection. Some people are kind of tired of it because we talk about it a lot, but it's our first. So I mean, it's my favorite. So on September 14th, 2015, we observed two black holes. This is the sizes of them. So 29 and 36 solar masses. What does that mean? So let's say we had a ball about the size of Toronto. And so a ball the size of Toronto, and then we threw in 30 suns into that ball. And then we moved, and we had two of them, and we moved them close to the speed of light and then smashed them into each other. That is what we observed. And that was over 1 billion years ago. So the Earth only had multicellular life on the Earth. So a long time ago. And this happened over 1.3 billion light years away. So very far away. So the signal was small. Well, it was actually big, actually, for us. And this happened on a Monday at 3 a.m. Louisiana's detector, let's back up again. So that red wiggly signal that we had, that's what we see most of the time. But in Louisiana, their detector saw this at 4:50 in the morning, their time. 7 milliseconds later, this is what we saw 20 miles away from where I'm at right now at the detector I work at. And so you see that there's something there, and you can actually take that data, put it on top of each other, and this is what it looks like. You can see that both of these detectors, 2,000 kilometers away from each other, saw the same thing. And you're getting information here. You're getting something like a signal kind of getting bigger. It's getting bigger and bigger and bigger. And then you're seeing like an oscillation. So you're seeing a wiggle that's getting faster and faster and faster. So the frequency is increasing. And so that's telling that data right there is telling you a lot of information. You could take that data, plug in parameters from that data into Einstein's equations, and then you get an idea of what caused it. And I think I have a video of that in a little bit, but let's jump ahead. I should just say, seeing this for the first time changed my life. It changed all of our lives. And so it was just a huge thing. So I try to think what it would be like, because I mean, I'm single. I don't have kids. If I imagine it's what it's like for a parent to see their kid for the first time, like the sonogram, like seeing that for the first time is what this is like for me to see that. Yeah, it's just life changing. We have people who work with us all around the world. And the first person to see that signal was in Germany, and it was about lunchtime. And this is an email he sent. I was at work the night before, and by the time I got home, my shift was at midnight. This thing happened at 3 a.m. By the time my head hit the pillow, that signal, and I closed my eyes, that signal passed right through the earth. It passed right through me, and it passed right through all of you. But because we're getting showered by these signals all the time. But for the first time, it was recorded, and this person sent out this email. So I woke up to this email the next day, and I was mind blown. Okay, so that data, we can also listen to it. Gravitational waves aren't sound, but it's an electrical signal, and it happens to be at a frequency that's our ears can hear. So this is what it actually sounds like. Here. Yeah. And so it's a big enough signal that that's just the raw data, and you could just hear it in our data. Here it is tweaked a little bit, so it's a little easier to hear. So like I said, you could take the information from that data, put them into Einstein's equations, and you could do a lot of things with it. You could listen to it, you can see what it looks like, and people who are good at programming can make movies about it. So here's what, so that data tells you stuff. It tells you where it came from, the objects that were involved. So there were 2 black holes. We know how big they are because of the data. And here's a movie of what it looks like. So yeah, 29 solar masses, 36 solar masses. These are pretty big black holes. This was the first time gravitational waves have been directly detected, the first time binary black holes, pairs of black holes have been observed. A lot of things, this was a huge discovery in 2015. And this is slowed down a lot. These things are moving close to the speed of light. So they're moving super fast, and they're getting closer and closer with each orbit and getting faster and faster. And then right at the end, if you look in the background here, these are the gravitational waves coming out. And the biggest wave happens right before they collide. We're slowed down a little bit more so you can see this merger actually happen. And you can see this pink, it's getting more pinker, which means it's getting bigger. And that's the big signal. Those are the signals that we want. We want really big signals because they're so hard to detect these things. Einstein thought we would never detect them. And so that signal is right there. This pink, this big burst is what we see. When those black holes combine, they formed a bigger black hole, and then it goes quiet because there's no more movement going on. That black hole is just happy, and those 2 black holes ate each other, and they just made a bigger black hole. I'm gonna skip through this. Okay, so this happened September 2015. We couldn't say anything about it because this was a huge discovery. So we had to analyze the data, write papers, and then get ready to announce. That took us time, though. It took us actually 5 months, but the news got out, and so somebody was tweeting about it. So we had to deal with this as well. Somebody was spilling the beans about our discovery. So I just threw these tweets in here. But eventually, we finally did get to announce, and that was in February of 2016. And that was cool because then we could finally share what we did with everybody, and that was an amazing thing for us. I think one of the coolest things about it is that just the reaction, the public's reaction, and just how media got into it, and just pop culture got into it as well. Really quick, so Ray Weiss is the person who invented the detector, and Kip Thorne is his buddy, who also came up with the idea of what we could maybe look for. So these are the 2 gentlemen who were kind of responsible for LIGO. And then, yeah, like I said, we were in all kinds of TV shows. The Late Show, we were on Saturday Night Live, where Von Miller said he tackled people like these black holes that crashed into each other. And here's, I forget his name. I don't watch the show, but I can't remember his name. He does work at Caltech though, but he has our data on his shirt. And then we were tweeted worldwide by everybody. I mean, let me see, there's Angry Birds, they actually tweeted about us. Our president tweeted about us as well. So it was a huge discovery. And so here we go here with the data. And somebody was crazy enough to even put it on their skin, get a tattoo of it. That was actually me. And so my tattoo is actually more popular than me. This is me back where I went to school, and people always like to take selfies. If I was doing this talk in person, we would be taking selfies. We would be taking pictures with my tattoo. This is LIGO and love in binary, so science tattoos, nerd tattoos. This is Dr. Jedidah Eisler. She's one of my heroes. She's an astrophysicist who studies supermassive black holes. And yeah, it was just amazing to get to meet her. And then I'm returning here to this because me and my sister got tattoos in Puerto Rico. This was right after we announced. So I had to go on a vacation, so we did that. We went to Arecibo, which is a radio telescope in Puerto Rico. That's me in the control room. That's me and my sister. I'm putting this up here because we just lost this huge radio dish behind us because this collapsed in December. It's very sad. This actually did gravitational wave work for related work as well. And so it's a kind of a sad thing, but I wanted to recognize Arecibo. Okay, so that's the big detection. That's the big discovery. I'm proud that my hands have been on the metal and glass of this detector, but I think one of the things that I'm even more prouder of, and I learned to get more prouder of, is that I actually recruited my mom and got to work with her. So a week before we announced, there was the discussion of our press release and drafting this document, the scientific document, and how we wanted to get it translated. We wanted to share this with the entire world. And so in a meeting about it, I actually talked to somebody and raised my hand and said, would it be cool if we translated it into Blackfoot? And people said yes. So I was totally surprised because we were still top secret. We couldn't tell anybody. So I recruited my mom and she translated the press release into Blackfoot. And I just have a couple of articles here, mainly about my mom and the work she did. This is on the Yakima Res, which is about an hour away from here. And this is an article about my mom here and her work. This is a Blackfoot paper that did an article about us. And then here is my mom at a conference that we both got to attend in 2016. And that shirt she bought is one that she actually had my coworker sign because she never met other LIGO scientists. So she was very cute. And then a few years later, a science reporter heard about this. And so this is a reporter I already knew about because I listened to this station, NPR, National Public Radio, all the time. And so Nell Greenfield Boyce called me up. And so she wanted to interview us. And I'd play this, but it just takes time and I'm kind of running out of time actually. So look it up. But the one thing I'll say about this is that a lot of people listen to NPR. A lot of people got to hear Blackfoot words. They got to hear Siksika. They got to hear about a residential school survivor. That's my mom. And those are the biggest things that I'm so happy about this and some other articles that my mom was interviewed for as well. And the other thing that I've learned to like is just learning to share our science and sharing how I connect indigenous culture, my culture into my science. So I did this way back in the day though, even before detection. So this is on the Yakima Res. No PowerPoint here. This is like something called a transparency thing. I don't know if people know what this is, overhead projector. This is like way old school. I'm old. So that's Yakima Res. This is the Nez Perce Reservation in Idaho. This is the Hoopa Reservation in Northern California. These are just places I've been to. This is, I was a mentor for Callista Spoon Hunter. She's Yakima, and this is at her graduation. And then this is a talk I gave in November of 2015. So this is at Humboldt State where I went to school, and these are high schoolers. And I couldn't say anything about this detection that happened just 2 months earlier. So this is my poker face. And then this is Flathead Lake. This is Salish Kootenai tribe students. And I'm putting that up there because this was back in 2003. This window here is actually right here. And then this is my kayak returning for my first time in the water with my kayak last September. I have like 10, 15 minutes. Okay, I'm gonna try to go through this, I think I'll try to do this. Okay, so that's the big detection. This is my second favorite one. And it happened in August of 2017, but not just the detection, something else happened. So my cousin Trudy Yellowfly and I, this is us at our powwow, the Siksika Nation powwow, which happens every August when there's not a pandemic. And we came up with the idea of hosting a grass dance special, a gravitational wave grass dance special, because I'm a grass dancer. I still grass dance every once in a while. I also sing. I sing Northern style, generally straight songs, no words. That's the old style, Blackfoot style is my preferred style of singing, which I love. So yeah, we wanted to somehow think of a way to integrate the science of Einstein and share it with at a powwow and let people know that people from our tribe are connected to Einstein because of the translation work that my mom did. And so we did that with a grass dance special. And here's, I think this is a flyer for it. Epuduk specia skest is the word my mom made for gravitational waves. It means stick together waves in Blackfoot. This is the special. This is where our powwow is at. These are all the grass dancers. This is me. I'm not a judge. I'm just observing, looking stoic and watching the dancers. And then these are the winners of the grass dance special that we had. And you can see we gave them hoodies as well as some cash. They were awesome. So I'm going to talk about my second favorite detection right here. So this is around the time of when it happened. So the colored areas are when we were observing and collecting data. These areas where it's not colored are when we're doing work on the detector. That's what we're doing now for the detector. We're working on it. And so observing run 1, observing run 2, excuse me, these are the detections. So there's one here. That's the big one. That's the first one. Another one. Here's another one. And then these are other detections that we made. This is a earthquake in Montana, July 2017. It's close to where I work. So it actually damaged our detector a little bit. So we were hobbling. We were almost, yeah, so that's what happened. That's just something to note. This is the day of the grass dance special up in Siksika. Right after that night, I had to drive back home for my shifts. I was on graveyard shifts, which is a good thing because that next week, a few days later, I was in the chair for my first detection. That's the first time I was ever in the chair for a detection on that Monday. And then here is the big one. This is a detection which is different than the 2 black holes that we saw. We see a lot of black holes crash into each other. This detection on August 17, 2017, was 2 neutron stars that crashed into each other. I'm gonna skip through this because I'm running out of time. This is just telling you how we look for detections and how we tell astronomers where to look in the sky. This is where I work a good chunk of the time. This is what the control room looks like. This is where the operators sit. So on that morning, it was about 5 in the morning, I received a call from the operator in Louisiana, and he told me to get on this conference call because there were scientists that were talking on there and they were screaming at each other, cussing, talking fast. And I was like, why? What's going on? And as soon as they said neutron stars, I knew something big was happening. And you don't want to hear, I'm going to skip through this. This is the detection that we saw. This is us. This is a satellite. That satellite saw a burst of gamma rays from 2 neutron stars crashing into each other. This is our data, gravitational wave data. This is light, gamma ray light. This, I'm going to skip through this too, just because, yeah. So I'm going to show a video of what it looks like in a movie, but this detection was seen by us. We told astronomers where to look with their instruments, point their instruments in the sky, and they ended up seeing this detection, these two stars crashing into each other in all different wavelengths. So this is that satellite. 8 hours later or 10 hours later, it was seen with visible light for the first time in Chile by this telescope. Then it was seen in infrared waves. Then it was seen in ultraviolet waves. And then it was seen in X-rays from this satellite. And then it was seen in radio waves for even weeks and months after it happened. So it was so much information came from it is because we told the astronomers where to look in the sky. And here's a video of it. So you have these two neutron stars, just like the black holes. It's the same kind of dance they go through. They're spinning around each other, and then boom, they crash into each other. What happens here is you get basically a couple Earths worth of gold, silver, all these heavy elements are generated from these collisions of neutron stars. So all this matter comes from them. And then we get all this other science that comes from it. And so a lot of stuff happened. We've been waiting to look for this type of detection. So binary neutron star detection, that's what that is, two neutron stars. That's my second favorite thing. So I'm gonna just go through a couple of other big stories that are related to us. So in 2017, a couple of weeks later, the Nobel Prize in Physics was announced from Stockholm, Sweden. I got up at 3 in the morning to watch this live, and the founders of LIGO were awarded the Nobel Prize in Physics. So it's a big deal. Einstein won the Nobel Prize also, many years ago. So it's a big deal. I didn't know much about the Nobel Prize, so I learned about it after this. I knew that when it was announced, I would definitely take my own vacation days and pay my way to go to Stockholm, just to go tailgate outside of the ceremony where these gentlemen received their detectors. So Ray, Barry Barish, and Kip Thorne are the awardees here. And of course, I took selfies with them, or I took pictures with them. I have to talk about Kip because Kip is, you might know some of his work. There's a movie called Interstellar. And so he worked with the Nolan brothers and he helped with the special effects for Gargantuan, the big black hole in that movie. So yeah, so he's kind of a big deal. And I'm also mentioning him because, back to Ray. I'm wearing a t-shirt from that grass dance special. I gave Ray a t-shirt as well. But with Kip, he actually read an article I wrote I never really met him before, but he sent me an email just like a few months ago, and he just talked about how he liked the story that I wrote. So it's kind of cool. So yeah, here we are in Stockholm, and I say we because as soon as I mentioned I was going, my family, they just assumed, they just volunteered themselves. So they went with me too. So this is a display at the Nobel Museum with my tattoo. This is where Ray, Kip, and Barry are at inside here. We're outside freezing while they're getting their medals, but we were having fun. This is me and my siblings here. And we're not holding the actual medal, we're holding chocolate replicas of it. So that's what this is. I'm hungry. The medals are actually about this big. They're made of gold, and Ray gave a replica to each observatory. So I've already taken, when things open up, you should come visit me, take a selfie with a Nobel medal, because they're a big deal. Okay, now I'm going to just talk about a few different other things, and then I think I'm towards the end. So what else? So one of my friends from college is, he makes comics. And so this is one of his comics about indigenous veterans from his tribe. You should check it out. His name's Cheg Lowry. We're buddies. We played basketball way back in the day. And so one thing a project we might be working on together is kind of sharing the story of my mother. And so that's what we have here. This is my mom. And then this is Einstein. I'm assuming this is me. That person looks a little too handsome to be me. Maybe a little too skinny. But that's a project that's in the works as well. And yeah, so advice. So I know that some of people in the audience are in high school. So this is mainly for you. I joke that I'm old, so I guess I'm an elder, or at least I joke about it. But this is advice that I've learned, and I like to share it with high schoolers and college students, or just people, because I didn't know some of this stuff. So internships, whatever you're studying, for the summers, look into internships, look for summer research, because this type of stuff you could put in your resume. You can do stuff that you're interested in and also get paid for it. It helped me get my job because it was in my resume. And when I was interviewed way back in 1998, they asked me about my research that I did. Find your passion, whether it's traveling or movies or kayaking. Find your passion and also connect it to what you're working on. So that's what I do because I love my work and I love being able to share it with you all. Yeah. Fail. I always fail. Like I'm going to fail now. I'm not going to be able to share everything I want to do, and I'm taking longer than I wanted, but I'm going to hopefully get through most of this. But fail is, I just like that. I like failing because it teaches you how to learn. It teaches you how to improve things and fix things. And then taking good notes and journal. I have notes all over the place that I have a pen here. I have a book here because you never know when ideas will come to you. And just be selfish. What I mean by that is just be selfish with your time. Don't be a slave to your work. That's what I used to do. But if you do that, you go crazy. So take time to go for a hike, get out in the mountains, or listen to music, go see shows, do when it's safe to do that. Yeah, you need that just to save your sanity. And then, yeah, just this whole talk is about how to bring yourself to work. And so this is an example, just one example, but I know all of you out there can do it in your own way. And then here are just some pictures of me doing some of this stuff. This is me salsa dancing with one of my friends. This is me at the Yakima Nation powwow with some of my salsa friends. This is my dog Gunner, who just passed away last year on a hike that we did together. Let's see. So what else has been happening since the pandemic? So we had observing run 3. That was our most recent observing run. So everything in color is when we were observing 24/7, recording data. And then here we have roughly all the detections that we have. I need to update this, but we cut things short because of the pandemic. But we did other work. We're working on the detector now. This is where we're at right now as far as detection. So these are 50 detections that we've made so far. All types of binary collisions that we've recorded. So each of them are different. Each of them have their own story, different size objects. Some of them are spinning in different ways. Some of them are far away. Some of them are fairly close, relatively speaking. But this is what we're doing. We're building up more information. Everything we've detected has been
5 minutes, Corey.
Okay, I'm getting there. Thank you. Okay, so let's keep on going. So what are other things that I've been doing during the pandemic? TikTok. So I've gotten into TikTok mainly as somebody watching it, but I actually made a few. So I'm going to show you a couple. So I got 5 minutes. I like hip hop, so I like it because it's short and simple. This is us moving a vacuum chamber at work.
9-7. Bust.
Follow me on TikTok.
Check it out.
That was in September. This is about a month or two ago. These are just optics that I was cleaning just a couple weeks ago. These mirrors are going to be installed into our detector. So I had about 50 of them to clean, and it's a little stressful to do it because you don't want to mess them up. Each of those things cost about $400, chunk of glass. Okay, so TikTok, it's helped me. Other things I have tons of time sometimes. So back in the day, I used to write Yelp reviews, and so these are 3 of the Yelp reviews I did for our first 3 detections. And I'm going to end here with a couple of just cultural things. So this is me and my mom. This was a talk I gave at a library. So I threw up a book that I liked, and the topic of hidden figures. This is me and my mom texting each other, and we're just talking about other hidden figures. And she mentions at the bottom just that there might be some hidden figures related to gravitational waves. So I thought that was funny. These are just other Indigenous people in science. So this is John Harrington, an astronaut. Ron So, he's Navajo. He works with LIGO as well. He's getting his PhD in astrophysics at Caltech. So he's a rock star. And then this is another Blackfoot astronomer. This is Rob Cardinal. He's identified comets and given some Blackfoot names as well. And then in 2018, I was asked to give a talk with Shemina Sid, Dr. Shemina Sid, and this is Angela, I can't forget her last name, but the 3 of us gave a talk, an Indigenous physicist talk at the SACNAS conference. And so from this meeting there, we came up with the idea of making a society of Indigenous physicists. And so here's our webpage. It's very new. This happened during the pandemic, and we get together for Zoom meetings, and we're just starting, and we're just wanting to increase representation of Indigenous people in physics, because a lot of us didn't have that. So we want more people to be interested in it, especially from Indigenous communities. Ways to join gravitational wave astronomy. There's different projects. So where LIGO is a ground-based detector. There's one in Italy called Virgo. There's CAGRA in Japan, but there's going to be a detector in space. There are ones that use radio dishes that are using pulsar timing. And then there's cosmic microwave background. There's another detector in the South Pole. And they're all looking at different types of sources. You could study physics, engineering, computer science. All of those are ways to get into gravitational wave astronomy. This is a new field, so it's very exciting. It's very new. So I'm just giving you the inside scoop. We talked about internships, grad school and postdoc is other ways to get into it. And then you could work with the project just like me. Talk to me. If you have any info, you can always, I'll give you my contact info coming up. Okay, I'm hurrying up. And then I'm gonna end on my mom, because that's where it all starts out. So this is my mom and my grandma. I just like these old photos. Like I said, my mom's a survivor of the residential schools. She took this picture here. This is the boarding school she was at. This is her at that boarding school as a person who has an anthropology degree, and she's looking through the rubble of it, and being the anthropologist, being a scientist, and looking at that, the sample, the samples or whatever, the wreckage there, in many ways than one. My mom and I have also spoke together. And so this is an Indigenous language conference at the University of Lethbridge in Alberta. That's Blackfoot territory. And we gave a talk together for the first time. And a lot of the audience were Blackfoot. So that was an amazing thing. And a lot of them were from Siksika Board of Ed. So we took a big group photo, and that was awesome. And then this is my mom visiting, and I took a picture of her over the X arm. And then I also recorded my mom right here at this table say that first translation, and it's on YouTube, so you could look it up. I have a few clips.
Mustis Gligo, Itapoku, Wis Udespumuk Mixisk National Science Foundation, NSF, Gi Mixisk Caltech, Gi MIT, Annixkai, Utquinipua, Gi Apistutimia, Gi Otuskia,
A big word.
Otwitsikatumia.
Yeah, my mom was a total soldier. I mean, it took a long time. It's only 15 minutes, but here's the end.
Mi Ligo, Neskskat Simia.
Yay.
Son of a biscuit.
Okay, so I'm going to end on this. Look, this is another outtake. My mom's so cute. I had to throw this in. So just...
What made you laugh?
I got the giggles. Okay, I got it.
Yeah, and I'm going to end here. So my mom and I gave a talk at McGill University in Montreal, 2019. And I went to go, this is a restaurant, we had dinner, and I went to go to the store to get something. And this is my mom just sitting on the patio there, and she didn't know I was taking this picture. And so when I look at this picture, I just think about my mom. She's a survivor of residential schools. She's this, this little girl who grew up in the community of Little Washington on the Siksika Reserve. And I just think about how this little girl from Little Washington was able to connect the Blackfoot words, with Einstein. She was basically a poet of astrophysics, and so that's what my mom did. And so I just think about that, and I'm always proud of it. And so that's what I'm going to end on, and I'm going to also share some of my contact info here. So you can look me up on social media, TikTok as well. But thank you so much. And yeah, if we have time, I would love to answer any questions that we have. Thank you.
That was awesome, Corey. Thank you so much.
Yeah.
That was so interesting. Wow. Yeah, we do have a lot of questions. I was just actually personally curious because I used to do a lot of astrophysics prior to my recent career,
Wow.
and
Oh,
I was
cool.
I was just wondering if you might have mentioned this as well, but I was wondering if you did any collaborative work with CERN or if you've even been there.
I have never been to CERN. So yeah, CERN is on the other end. Wait, is there, I don't, there's probably, I mean, there's ways that, so CERN is, for those who don't know, is a large accelerator. So what they have is this big ring where they basically run particles around this big ring, which is several tens of kilometers, I think, in diameter. And this is looking at this is particle physics. So this is the physics of the very, very small. And so it's different from what we do because we're looking at the physics of things that are very, very big. And so I've never been there, but the thing with what's in the future that's exciting is we want to connect the science of the very small with the very big. So that's what physicists are doing now. So that's what a lot of the like the young people in our audience, they might be interested in doing these and solving these questions because that's where the current work is kind of being done now, to connect all these theories together, because right now they're separated, and so we're trying to meld them together, mold them together.
That's so cool. That was just a personal question. I was just wondering, but
I want to go there. I want to go there.
I thought maybe you might have been there, you of all people, but
No.
okay, so let's get into some of our questions. You might have answered some of these already
Okay.
indirectly, but the first one was, what was your greatest discovery?
The greatest discovery, yes, I kind of already did talk about that. Those two detections that we talked about. So that sometimes I forget the date sometimes, so that's why it's nice to have it on my skin. So GW 150914, so September 14th, 2015. That detection that's the greatest one because I mean that's the first one. It happened 100 years, almost to the month of Einstein's presentation of general relativity. That's the one that got the Nobel Prize. So the firsts are always the best. So also the binary neutron star, that's another one. But there's going to be better ones. There's going to be ones that are going to be surprises. So that's the one. Those are the ones I'm more excited about next, I guess. So other possible detections that theorists have thought about are supernova explosions. So if there's a star that explodes close enough to us, that will emit gravitational waves. And if it's close enough, we should be able to see it on our detectors. So that'd be something totally new. But even more exciting than that would be a signal which we have no idea about. So if there's something that comes on our computers and we're like, what is that? That could tell us something completely different. So that's why gravitational waves are so important, because gravitational waves are completely different than all other astronomy. So everything else in astronomy comes from light. So visible light, infrared, ultraviolet, all that stuff is effects at the atomic level, whereas gravitational waves come from the actual objects moving around each other. So that's why gravitational waves are so different, and that's why I'm into it.
Awesome. Next question is, how do you tell how far away like the signals come from? Like you mentioned that they were several light years away sometimes. Like how can you tell? Is that like how do you tell that?
It's basically kind of like triangulation. So it's time of arrival. So for that first detection, I kind of mentioned how Louisiana saw the wiggle first, this gravitational wave signal first, and then 7 milliseconds later, it happened in Washington State where I work. So that kind of tells you, oh, that signal came, I don't know if you could see, I don't know if I'm saying, anyway, so wait, if you're looking at me, so this is Washington and Louisiana. So they saw it first and then we saw it next. So that's telling us, oh, that signal came from that way. And so that's one thing that tells us how far out it is. But the other thing I also kind of related is that, why do you want to have multiple detectors? The thing is that if you have more detectors on the planet, so there's the 2 LIGO ones, there's Italy, there's Japan, all of them are going to receive the signal at different times probably. And because of that, helps you tell where in the sky it's coming from, depending on this signal, this detector saw it, and then this one, and then this one. So they're going to kind of limit where that could be coming from. And so that is so important because it helps astronomers point their instruments. And that's why that binary neutron star was kind of cool because that was it in action. We got to see that example in action. Good question.
That's so interesting. Next question. Is it possible to know where a black hole goes to?
Yeah, where a black hole goes to. So that's what we're just going to learn about that, because we're just making a catalog of all these detections. So what we're looking at are binary collisions, but like what happens, we're seeing, like with all of our detections, we're only seeing the last fraction of a second of the dance that they had. But what happened before that? I mean, they were doing their own thing. There might be one black hole that was just chilling here, just like looking around, just doing its own thing, not doing anything. But there might have been another one that just happened to pass by and captured it. And then now they're both in a dance, and they're going to be spinning around each other for, you know, millions of years, generating gravitational waves, but they're very small. And it's only at the very last second that we see it. So we're kind of learning about the lives of black holes. And there's already science that we're learning with some of these detections that we made that are making people scratch their heads, because it's kind of new science. And that's what we're trying to do, learn the life of black holes. So yeah, that's something you could answer maybe if you're interested in the subject.
Yeah, definitely. Next question is, how does being Indigenous influence the work that you do now?
I know, yeah. I mean, I think it always influenced me, even from the beginning. Like I said, I mean, back in the day, before this was just a job where I turned a wrench or drove a forklift or operated a crane, I'd come into work and just get ready for my day. But before coming into work, I might be blasting some power music. So I let people know I'm Indigenous. I mean, and if we like I do talks and stuff like that, but that just representation is just a huge thing. And so that's something I always think about. And I know a lot of my fellow Indigenous physicists also think about it, because just representation is so important. So that's the main thing I think about with my culture, just to get out there, even though I was a shy kid, even though I was shy back in the day, and I'm still a little bit shy, maybe not that much, but I just think it's just so important for us to get out there, because for a lot of us, we didn't have that when we were studying physics way back in the day.
Yeah.
I hope that answered the question. I'm not sure.
Yeah, no. Yeah, I feel that for sure. Next question. Why? Oh, this is a good one. Why did you have to keep the discovery a secret for so long?
Yeah, that's a very good question. So, and I could tell you how we evolved on that, because we didn't want to be wrong. We wanted to make sure that this was a real signal. And so that's why we took, and this was the first time it ever happened. So you want to make sure for the first discovery that it is totally real. And so, yeah, so what happened that morning? I think everything was crazy that next morning. My boss basically told everybody to not touch anything, because sometimes we would go do maintenance on the machine, but we said, let the machines run, record data. We're not going to change anything for weeks, because we want to keep collecting data and just make sure we have a lot of background data to compare to this little tiny, fraction of a second where we saw the signal. So there's that. So confirming that the signal was real. What else? And then that took like a few weeks. And then writing the paper actually surprisingly took a long time as well. That took like the paper, you can look it up online. It's only about 4 or 5 pages, and it's actually decent to read. It's not that hard to read, but it took a long time to write a huge, century in the making kind of discovery paper. And so that took a while. And then what else? And then the collaboration we work with has about 1,800 people. So you have all these different opinions. So when you're writing a paper, you have to deal with all these opinions as well. So yeah, so confirming the signal is real, and then yeah, writing the paper and all that stuff. We want to just make sure that it's right. And so that's why it was stressful to have to deal with this person who was tweeting about our announcement, because they're trying to get glory there. They're trying to like steal our spotlight and trying to get us to say stuff, but we don't want to say it until we know it's real. And that's just kind of how science is. We want to be peer reviewed by other people who are not a part of our project. And there's a process to announcing, especially for first discoveries like this. So yeah, it took a while. It was stressful. That's when I probably gained like 15 pounds. I gained like, I got fat. I'm still fighting that.
Interesting. Okay, interesting. Was Interstellar accurate, the movie?
Interstellar is cool. I mean, it's actually very, it's awesome because it's out there in the mainstream. And Kip Thorne actually had, yeah, he wrote a paper for that's the CGI that was made for Gargantuan and the wormhole that are in the movie. So all that science is going to definitely be real. I remember hearing rumors about this movie back in the day, and I think Spielberg was the first person to maybe who was thought of to direct it. But then, yeah, it changed into the Nolan brothers. But you know that if Kip is tied to it, that the science of the black holes would be accurate. And the way that they talk about how time is different with regards to where you're at with regards to the black hole. Like if you're closer to it, time moves a lot slower, and you get to see that with the characters who are on a planet near the black hole where time is slower versus one who's in orbit around them, and you could see how time is different. And that's just because of how crazy gravity is because of freaking Einstein. Einstein just seemed like an alien, just the way he thought of that, because there's hardly many cars on the roads when he presented that his general theory of relativity, and still so much science comes from him.
Interesting. Okay, well, last question. Has gravitational wave detection created new and or puzzling questions, or has it further enforced your understanding?
So a lot of grad students, one of their goals is to test GR, so test gravitational waves. They want to see how strong Einstein's field equations for gravity are. And so far, with 50 detections, we have not come up with anything that, finds a weakness in GR. So that's one thing. But new science would be definitely from the binary neutron star collision. I mean, that one we got to learn about the constraints for the expansion of the universe. So that's a constraint that we were able to provide to science. What else? One of the black hole collisions from the most recent observing run happened to involve a black hole that was bigger than a lot of scientists thought could be out there. And so their thought is that black hole was probably built by other black holes that crashed into each other, and that's how it got to be so big and crash into another black hole. So this whole idea of black holes merging into each other, we're just learning more about it and how they evolve. So that's new. That's kind of new. That's coming from us. And another detection also from the recent observing run was this mystery object. We had one black hole, and then we had another object, which was a size that it was a mystery. It was either going to be the smallest black hole or the largest neutron star. We don't really know that. So we need to make more of those types of detections to determine that. So yeah, it's kind of cool to see how science might be changing. Textbooks will be changing because of this work.
Yeah, so you're saying it's kind of like a little bit of both. Like it's created new questions, but it's also helped you understand more about other things too.
Totally. So that's why it's so important for the youth to like get interested in this, because there's so many answers that need to be answered.
That's really awesome. Thank you so much, Corey. That looks like all the questions we have. That was a lot of questions. So thanks for that.
Okay, good.
And thanks everyone for joining us.
Yeah.
Corey on all of his social media that's up here. And we will see you next week for building.
Awesome. See ya. Okay, later. Thank you.
Bye.